Good morning, everyone. Welcome to our Spartan series presentation. I'm Paulina.
And I'm Justin. We're presenting on the complexity index and our design philosophy. And we're both mechanical and manufacturing students.
Okay, so our first major design philosophy is to revolve around flexibility. And on our team, this looks like a variety of different things. But one of the major things that we care about is being able to work on one subsystem whilst finalizing the other and putting that through manufacturing and beginning to actually make it. So we try to prevent full robot iterations. And we just want to be able to edit on such as this year on our arm, we wanted to work on our intake and end effector system while still starting to manufacture the arm.
Yeah, so a lot of the time we like to be able to fine-tune things at the very end. So for example, for our intakes and shooters, a lot of the time we have servos or a really high gear ratio, so we can really fine-tune all the angles at the end when we have a lot more time to do testing for to find the perfect angle for an intake or a perfect angle to shoot a certain distance. It allows us a lot more flexibility, especially if we're able to change it in software, which is a lot more flexible than not being able to do it at all, and hardware limited, which you have to do a lot of revisions and a lot of iterations in manufacturing to fix.
Another one of our philosophies is to build a more robust robot, and that sounds pretty straightforward, and obviously all teams in general would want to do that. And this helps us minimize our repair and building time. For example, we try to use more structural adhesives rather than welding, so we'll epoxy things on our drivetrain together. Just so that if something were to break at competition, which it actually did happen at Monterey Bay Regional last year, we were able to take off the parts, re-epoxy it, and then put it on so that the next day we were able to be ready and use it. Rather than if the welding were to break, we wouldn't have any means of fixing it during competition.
A quick note about using structural adhesives on epoxy is you have to design your parts to be able to use that. Because a lot of parts, if you have really little surface contact, the structural adhesive and epoxy won't be as strong as welding. But if you have a lot of surface area, it'll be pretty much as strong. Also, you have to make sure you have rivets to do pulling forces, because epoxy is really only good at shear. Yeah.
And if you want to hear about how we use that, there's another Spartan series presentation about it later today. But going on with robustness, we also do a lot of gearbox calculations, almost for every gearbox on the robot. And also this year we did a lot of calculations on our arm beforehand, so that it hopefully wouldn't break during the season, and it didn't. But that's just one of the other ways that we try to create robustness.
We also like doing things that are easy to implement with little disadvantages. This may seem pretty obvious, but we tend to do this in different ways. For example, we use materials like wood that most other teams might not use. So for example, we used it as a cover for our 2022 robot, where there was a bigas chain on it that just went on it, and wood was perfectly fine because it was rigid, it was strong, and it cut down a lot on our manufacturing time, and it was pretty light.
Another easy to implement change that we've been doing is, rather than manufacturing our drive shafts and all shafts in general to specifically fit all of the sprockets and gears that go on it, we've been actually gluing our shafts together and gluing everything on the shaft to it to prevent backlash, rather than having to manufacture the shaft specifically for that. And it's been able to save us manufacturing time, and that's really important during the season.
We also design our shafts in CAD to be an easy length to make, and then we can easily 3D print custom spacers, because you can do that all the time without a student there. So we design a lot of things so that we can just 3D print something and make the parts that we actually make manufacture like out of metal a lot simpler.
Design for excellence is a term that covers like many like smaller philosophies listed below. There's design for performance, controllability, reliability, manufacturability, assembly, and serviceability. So this is something that we kind of, when we're doing the design phase, we're like making our parts and mechanisms to go around like this philosophy. For example, for serviceability, this is a picture of the 2022 turret. And because the turret was so centralized in the middle of a robot and there's a lot of stuff around it, it's not very accessible to repair and stuff. But what we did was we created space so that we can repair it from the bottom of the robot by flipping the robot sideways. You can see here the tensioner is very accessible from the bottom, as well as the potentiometer and mag encoder, respectively, in the cyan.
We also, if you want to learn more about this, we did a Spartan series talk last year about designing for manufacturability, the four on the right there. Our last value is we like to have fun. We like to challenge ourselves, make unique and new mechanisms. So we're really open to different like new ideas that may seem out of the norm, like using suction or using a double jointed arm or having a pivoting shooter.
So to recap, our 5 major philosophies are flexibility, robustness, value, design for excellence, and fun. Okay, so now we're going to go through a bunch of like mechanical decisions and like things that we've done as examples for these values, just so that you know how you can implement them on your team.
So this year we chose to have a double jointed arm because it really allows us to have a lot of flexibility in our end effector, so we could really design all our double jointed arm and all our gearboxes way before the prototyping for our end effector and intake are done. So we can make that and be more efficient. The double jointed arm also allows our robot to be really robust. We can put we can design it really well to make like some really solid joints with big bearings and cross roller bearings. It was also kind of a design challenge to update our 2018 arm, make it really stiff. There were a few flaws with our 2018 arm that made it wobble, but not as rigid as we wanted. So we revised that this year. Yeah.
So why do we use a capstan? For you guys that don't know, the capstan is like the part over here, kind of like a sprocket, but instead of using chain, it's for cable. And we use the capstan because it removes weight from the arm, but so that we don't have to put the gearbox on the arm itself. Instead, the gearbox for like both joints of the arm is at the bottom over here. And cable we've also found that it was stiffer than chain because we didn't have to have as large of like a pulley size for the same rotational stiffness. And this was important to us because we wanted our arm to like not oscillate or vibrate very much, to just make it more stiff overall so that we could have better like game piece placage. It's also easier to tension the cable compared to the chain, because for chain you have to either incorporate like a tensioner like into the chain itself, but for cable you're able to just tighten it more on the bottom or like either side.
If you'd like to know more about how we went through this design process and chose like a capstan, there's a arm design and calculations Spartan series that's going to be in the next session. So last year we used a catapult on our robot instead of a flywheel, and some of the key things that we found that we liked better with a catapult was that it was a lot more consistent. You can control a lot more variables. It doesn't have any backspin, and like ball pressure and like squish doesn't really matter between balls since you're just catapulting it. And since you can only hold a few balls, it doesn't really matter that the speed between like shooting each ball didn't really matter as much. It also helped keep our center of gravity low because you can keep the catapult really low. You don't have to have like a tall shooter or accelerator tower.
Elaborating a bit more on the variables part, we found that like with the catapult, we were able to release, or we didn't have to predetermine like while we were designing it exactly what angles we had to release at and what velocities, but instead we were able to test it later, which kind of goes along like our flexibility point. By doing this, we knew that we could kind of solve it in code at the end, near the end of the season, rather than having to spend time at the beginning to like make it mechanically, and like if things were to go wrong, we'd have to have revisions for it.
On the same point, a catapult's actually a very simple mechanical mechanism. It's just basically a motor connected directly to like the arm. So it was really easy for us to design that and fit that into our design constraints for the rest of the robot. So we have we've made our own operating system for each like part of our robot. So each Raspberry Pi or CPU essentially runs our custom software operating system. And this really allows us to decouple development so you can work on different parts of the robot like the IMU and the vision at the same time. It also makes you able to have like different loads spread out the load across different processors because the architecture is very distributed. It uses PubSub, which is a publication subscription, which basically allows you to asynchronously communicate. And also, we designed this to be really easy with introspection, so everything is logged, all the messages, so you can reconstruct everything that happened in a match after, and this allows us to fix a lot of the bugs that we find, and we can fix a lot of the bugs we found like during a competition, and we can easily rerun and see what was happening at every moment. We also designed it so we can like simulate the code with each module. So essentially, you can either test it with the robot or you can simulate it. And we have a lot of test cases to make sure that those are really similar. So if you fix something like a bug you found, you can test it with the code and you can see like the immediate results to see if it fixed the problem or did what you were expecting it to do. And this overall just allows us to make a lot more complex and custom code for some of the mechanisms that we do like that are not in the norm and are a little different.
Something else that we do are custom PCBs. And this is really important because it allows us to like make a universal Molex connector for the whole robot rather than like soldering all the connections. So this, like, if we were to go to a competition and we needed to like rewire something, we didn't have to like directly do work on the robot, and you could parallel path it by like creating wires in the hand and on like separately and being able to replace them easily. It also like improves our reliability because the wires like don't disconnect nearly as easily, and electrical problems are something that we found to be pretty impactful to us like during competitions. And it also lowers the complexity of wiring because you can start like cutting and doing the wires separately like before rather than having to solder everything right like when the robot is being wired.
So for example, this year we made custom PCBs for both our mag encoders and pots so we don't have to solder them every time. We can just clip them in. So it makes it a lot faster just to swap out if a mag encoder or a pot breaks, and we can just take another one, put it in, and then plug it in. And it's a lot simpler than having to resolder it every time.
For this year's ARM, this is also really practical because we had something where we could replace both the end effector and the arm. And because the wiring goes along like to the very end of it, if you were to replace like a component of it, you could just easily unplug it and replug it.
So we also have a custom IMU PCB that we've made. We designed this to use a more accurate IMU so we can get better full field localization. And this is really important to us because we didn't have this in like 2019, and our vision incorrectly identified a hatch panel because we over-relied on vision then. So that ended us losing and not making it to finals. So we've really pushed for having good localization. So that's why we've made this custom IMU chip. Some of the other things it does is it does like sensor fusion on board. So you can plug in all the mag encoders or like pots for like drivetrain and other mechanisms that may affect movement. It can combine all of them. I believe James is going to do a talk on the software behind that, which is another Spartan series that's happening sometime, I think at the last session. And so this kind of fits in with the AOS where every like processor is decoupled. So someone could have worked on this at the same time as something as like the actual robot code or like the drivetrain code. So it allows us to be really flexible. It also reduces electromagnetic interference because it has opto-isolators and kind of like separates all the electrical currents. This just makes our robot a little more robust and our localization more reliable.
Going along with like our localization, we have 4 cameras on the robot right now, and they're all rock pies, and this gives us like a 360-degree view around, so that at all times we can reference off different like April tags and different landmarks on the field to know where we are, so that we don't encounter the same problem we did in 2019 again. Okay, so transitioning into like the second part of our presentation about like a complexity index, we've always like had the question, how many DOFs is too many? Like, how complex of a robot is something that we as a team can't handle? And this is a sticker from this year. We can pass it out at the end. But it just kind of like encapsulates yet another design philosophy, which is that every DOF saved is a DOF earned. So I guess as a team, we're known for creating like, overly perhaps complex robots. But we do want to limit ourselves to that. So we'll be going into like how we decide what we can make.
So first, what is a DOF? A DOF is a degree of freedom. It's essentially like an or movement that a robot can make. It's very similar to like physics degrees of freedom. So for example, a drivetrain has 2 degrees of freedom because each side will rotate. Well, a tank drivetrain will have 2 degrees of freedom because each side you can rotate independently of each other.
Like in space and physics, there would be 6 degrees of freedom because 3 axes and each of them would have like rotation around them.
So our complexity index this year we've updated. So for each mechanism we give a degree of freedom score. It's basically 1 is for very simple, 2 is for like a normal one that would take like an approximate time, and then 3 is like a lot of prototyping or a lot of manufacturing or like needs a lot of integration. And basically the complexity index is meant to like quantify how long it would take our team to make something. So usually it's a good relative to like a complexity and to each mechanism. This year we added a duplicate mechanism also score because sometimes when you duplicate a mechanism, it can also make your robot a lot harder to make. So we give 0 points if it's like purely the same and it doesn't affect anything. We give a few more points if it needs a lot more manufacturing or needs a lot of integration with other subsystem, or if it affects like all the other subsystems because it's going to push our robot weight over the weight limit, or needs a lot of like integration with the others. And then combined with that, at the end, we have a multiplier from 1 to 2, which is how likely it'll need like revisions. Like for example, an intake would get a multiplier of a 2 since you need to update that, revise it, and test like a lot of different geometries. But like a drivetrain, you don't really need to test that. You can do most of that in CAD. So that would just be a 1.
Something pretty important to emphasize is the duplicate mechanism complexity index, because in the past we've had experiences where we thought like, oh, so in 2022 we had a double intake, so we thought, okay, both sides of the intake both intakes are identical, and there's no reason that it should be like an extra degree of freedom, extra complexity. But what we realized was that because the second intake, like we had to turn the whole turret around in order to get balls from that intake, and the intakes were pretty fragile and we had to make a lot of them, it cost us like a lot more time, and this wasn't something that we had accounted for, but we found it to be pretty challenging.
So some of the thoughts that we put into this that you can, if you want to make your own complexity index, is to think about what your main bottleneck is. Like for us, it's manufacturing. So we have not as advanced machines as some of the really top teams do. So we do take a longer time. We have our own custom CNC router, which does break sometimes and takes some time to fix. So we also include that into like how long it would take. We also have a limited amount of experienced students with manufacturing, especially with some of our complex parts. So that takes a lot of time. So that leads us to like the other points. How experienced are your students? How confident do people feel to be able to lead like a subsystem or to code like a part of the robot? So you can go through like each part of the design phase. The design phase is like mechanical. How long will CAD take? How long will manufacturing take? How long will wiring take? You can identify like how long each of those take and give different weights based on which one your team is most confident in. And also something to be aware of like Paulina talked about, is zero DOF systems, like duplicate mechanisms or ones that aren't like powered. They can sometimes take a lot of time and development because of their integration. So just because it's zero DOFs doesn't mean that it doesn't take any time to make.
This is just a more detailed version of our complexity index from this year. I think that it might be helpful for you to take a look at it, like when we post the slides online at some point. But it was pretty much summarized in an earlier slide. I think that we didn't go over this, but the DOF score, you just need to multiply it by the multiplier and then add it up to find out the complexity index of each mechanism and then your entire like robot.
So we wanted to go through this process with our robot this year. Does anyone know any of the degrees of freedom of our robot this year? We called the joint down there the proximal joint since it's closer, and the distal because it's farther. Some people may not know this, but we also have a wrist on the end effector, which basically rotates the two rollers. So we actually do have a 5-degree of freedom arm. Yeah.
The end effector wrist, basically it allowed us to pick up like the cones and cubes at any orientation and then rotate it so that like if the cone were sideways with like the point facing away, we would pick it up by the flange and then rotate it 90 degrees before we place it onto like the peg. And now we'll be analyzing the 2023 robot complexity index.
So to begin, our first mechanism was the drive chain. This year we gave it a DOF score of 2, and the reason is that it's very similar to past years, but we had to accommodate a lot for the other systems in our robot design. So for example, we had to add ballast and shift over weight as far over to the other corner of where the arm is to offset the center of gravity. The proximal joint, we gave a DOF score of 3 as well with the distal joint because they were really hard to integrate, especially since we had like nested bearings. But it didn't take much prototyping. We could all see it in CAD and do all the math before to make sure it was good.
For the roll joint, we gave it a DOF score of 2 because we had to integrate it with the other joints, but it wasn't super complex because there was no like big gearbox that we had to design. For the end effector, we gave the roller a DOF score of 2, but it had a multiplier of 2 because we had to do prototyping at the beginning of the season. We prototyped horizontal and vertical rollers and just a bunch of end effectors. For the wrist, we gave it a DOF score of 2 because we had to make it relatively light and design around that. To summarize our presentation, we first talked about design principles, the first one being flexibility, which is designing things so that we know that we can continue working on other parts of the robot that interact with that subsystem in the future while it's like being manufactured or things like that. The next design principle is robustness, so just designing so that we don't have to keep maintaining our robot between matches. Value is just having fewer drawbacks. We talked about using certain materials such as like 3D printing and also like epoxies and glues. Design for excellence is an overarching term that encompasses designing for manufacturability, assembly, other things like that. And lastly, fun, because FRC is all about fun.
After that, we went over our complexity index, which is meant to be able to quantify how long a robot would take to build and how much it would fit in your schedule. It's mainly based on each degree of freedom, and there's a multiplier for how long it would take for prototyping. And this can vary depending on each team.
So how do you tend to manage complexity with time deadlines? Like, for example, knowing how you want to divide up your build season by CAD team hands off to build by this time, build hands off to program by this time. How do you figure out how complex you should make the robot based on hitting those sort of target allotments of time? And how long are those for each sort of section of your team?
Yeah, that's a great question. So we've been a team for a really long time. So we have robots from past years, and we've been kind of just looking at like, okay, so last year our complexity index was blank. We had like a certain number of students who were like committed and experienced. We had like this kind of machining capability. So basically we were looking at like past year's robots to see if like things have changed with our team and if we can change the complexity index that we're looking for. And towards the part of your question about setting timelines, like we generally try to have the same timeline every year where we spend like around, or we kind of parallel path things. So like the harder subsystems, or not really harder, but the ones that take more like hands-on prototyping, we'll like still be prototyping that by like week 1, the end of week 1, whereas the other subsystems will be doing like CAD or CAD. And then we generally do design for around, I think, 2 weeks or maybe 3, edging into 3 before we start like manufacturing. But like, of course, when we start manufacturing like an earlier system like our drivetrain, the later ones, such as like end effector and parts of the arm, are definitely not done yet.
So like what kind of manufacturing resources do you have access to? Like the capstan pulley, like how did you manufacture that?
So for our capstan pulley, we designed it to be so we can make it in-house. So essentially it's like basically a bunch of stacked up plates, which we can cut on our CNC router. So we have a CNC router that we made in 2016 that's custom. We have an email that has 2 axes of CNC, and we have 2 lathes. And those are basically the main manufacturing for parts. We also have like a few of the other simpler machines, but we don't tend to use those as much. So for our capstan, like I said, we designed it to have like different sections, so we could just use our router to cut each of those sections. And we just stack it up with dowel pins and screws to make sure that they align for shear load and to be clamped.
For more complex parts, do you ever outsource manufacturing or just generally tend to avoid anything that would be beyond your capabilities in the design process?
We like to avoid doing that, but we do sometimes outsource our parts. Like for this year, let's see, 2 parts on, so this part here and that part there, those were outsourced to one of our sponsors, Blue River, to make because it needed a 4th axis. But for those parts, we also had like a second like plan to make it in-house. It just wouldn't have turned out as well, or wouldn't have been as simple. Yeah. All the other parts are pretty much made in-house. Yeah.
What are you guys' philosophy on the structural integrity of 3D printed parts versus normal metal machine parts?
So the question was for the recording, like what's our philosophy on the structure of our 3D printed parts? So first, we have a lot of 3D printed parts on our robot. For example, over here, like the end effector is clamped onto the carbon fiber tube via just like a 3D printed clamp with like around 13 screws in it, which kind of also goes around with our like easy to replace kind of thing. But for this part, like we use onyx for all of our 3D printing, and we found that to be like pretty structurally sound. But sometimes when we want it to be even stronger, we do like put carbon fiber, or like put like fiber inlay like within the 3D printed part. And we're also pretty lucky to have like several Markforged 3D printers that we can use for this.
For more direct example, like for these two parts that we machined with a sponsor, we made them out of metal because we weren't that confident in we haven't investigated the complete structural integrity of 3D printed parts. But you probably could design a 3D printed part with fiber inlay to do the same job that the metal part did. And we're in the process of investigating further how strong 3D printed parts are, and we want to introduce more of those in our robot next year.
How much does making the practice robot help during build season, and what do you use it for?
So practice robot during the build season really helps us have 2 robots we can use. So we tend to have a heavy emphasis on drive practice. So one robot could be used for that, while the mechanical team does a revision on the other robot and make sure that it works, and then you can just swap them. So we'll always have a robot that's up and running. The same goes for we can give one to software, so that they can use that one to do all their testing, while we finish making the other robot or doing a revision on the other one. We find that it's really efficient. And also, if one robot breaks, you always have another robot you can use. But it does take a lot of extra manufacturing time to make 2 robots. So it might not be entirely worth it, but we find that it really works, really helps our team.
So you mentioned that integration, difficulty of integration was one of the measurements to the complexity of mechanism, right? So how do you guys integrate your mechanisms in CAD? Do you try to design it in parallel, or do you just have a modular design that that goes together later?
So at the start, we do something called Crayola CAD, which basically is just claims space, so you know where different subsystems might interact and might have space constraints. So the subsystems will take that into account, and then we'll kind of talk about how each subsystem will work with each other, the ones that are at least touching each other. And then after that, we use Onshape. So we have a separate document for every subsystem. So it might not we don't design them all in the same document, but it does allow us to derive in a part studio parts from another subsystem. Then we can use that to model around. So we do a lot of using derived features to make sure everything lines up, and then we edit one system and subsystem, and then we can update it in the other one and making sure everything fits. And then we also have a main assembly at the end where we basically connect everything and make sure that everything doesn't hit other parts.
And we found that splitting our robot into sub-assemblies within Onshape is really important to us, because when we have too many people on it, it gets really slow and just not convenient or a good use of time.
Yep.
How do you tend to handle interdomain design decisions, for example, where to place a sensor, since that would affect both code and mechanical and CAD?
So for a lot of sensor placement, we tend to decide that the start of the subsystem. We have a meeting between software and electrical, and making sure what's best for each each part. And we kind of choose the rough location where we want it. And then a lot of the times you can design around that. But sometimes you have to make a compromise between which one's better and which one's more accessible.
Our team does, everybody on the mechanical sub team will go through the process of CAD or prototyping, and then CAD, and then manufacturing, assembly, etc. But I know that on some other teams there's a special CAD sub team and then manufacturing. Yeah, so for us it's just the same people, probably some of the subsystem leads will talk to the software subsystem leads and ask where they would like it. On the end effector specifically, there were some sensors that allowed us to know if our where the cone was or where the cube was within our intake. Yeah, so basically just tight communication between software and hardware.
Another example is for our ARM gearbox. At the start, we talked about like what sensors we wanted, and we decided we wanted like both a potentiometer and a mag encoder to get like some accurate like angle and like localization. So we decided that at the start, and that so then we mechanical tends to know like where it's best. So we really want it to be close to like the furthest output shaft for sensors, so you get the most accurate reading of what actually happens, so you don't have to like as much backlash. So a lot of the time we know that and we take that into account when we design it. So that would make it a lot easier. Yeah, does that answer your question?
Why did you decide to drop the midsection of your bumper?
Hey, so
Yeah.
the theory behind dropping the section of the bumper, we call it like a boat bumper. So essentially, when a robot pushes you from the side, if you have a really high bumper, it also pushes you up, so you get like less traction to get out of a pin. So that's why we lowered it. But also on the sides, we elevated it so that you could also get on the charge station really easily. Because if you had low bumpers, it'd like hit it, and you might get like stuck if you're at really low speeds. I will say it's really hard to make those bumpers.
Yeah.
It's not fun.
This is something that like we kind of had to do because of our tank constraint, but probably if like obviously if you have a swerve bot, this is like not really necessary or practical. Any other questions?
I have one.
Yeah.
So like in 2022, like you mentioned how you decided to go catapult because like you can, it's like basically infinitely adjustable. But like if you had like a hooded shooter, like you can design it just like at the very beginning to be able to shoot from the fender and then all the way back. Like so, like basically why do you not shoot for a middle ground?
Wait, what do you mean by like a middle ground?
Like in terms of like mechanical, like software adjustability and like mechanical, like complexity, I guess, or like.
Yeah, so that's a good question. For us, we did prototype like a flywheel and like a hooded shooter, but we found that like specifically for like shooting these balls, we like hung up like a pool noodle hoop outside and prototyped it, but we found that there was not really like a significant difference between like getting our catapulted balls in versus like the shooter. And also our software team like really enjoys having like a bit more of a challenge with being able to like do things in software and fix things in software. And also it kind of goes like we try to do like things that are not just the same every year. And we wanted to like try something new by doing like a carbon fiber catapult because that sounds fun, and like students got to learn how to work with carbon fiber, things like that. So when there's like not a big difference, we'll like go with the one that may be more interesting or innovative.
And specifically in the catapult case, we also found that it controlled variables more like less like the ball wouldn't affect how the catapult shot and like how far it would go. And there's like no backspin on the ball, so it won't like go out depending on like where you score. Does that answer your question? Yeah.
So how do you guys design around anti-defense? Like, how would you design your robot to make it less accessible to defense?
This year, like for our drivetrain, we had 6 Falcons on it. So basically we gave it like a lot of pushing power as well as speed, so that if like other people were to defend it, so that we wouldn't have to like struggle with keeping up with how fast Swerve was. And we do like generally things within drivetrain to fix that because of like everyone else being Swerve, I guess.
We also put a lot of design into our bumpers, like the boat design. We also prototyped last off season with like a more slippery material. So if you feel our bumpers, they're, at least this year, they're a lot more slippery than like other bumpers. So that's something else that we invested in. And also like using like more higher traction wheels At least, yeah, that helped us try to avoid defense or get out of defense.
We also tried to keep a lower CG, like again, moving as much gearbox and motors as we can like down low, and also putting like steel weights at the bottom of our belly pan, so that we wouldn't be able to tip as easily given like the tall parts of our robot.
For COTS components like motors and sensors and even prefab subsystems, do you have a particular method for choosing which one to use, managing complexity of integration, programming complexity, feature set, that kind of thing?
Sometimes when we try newer things, we do it like on our off-season robot. Like sometimes we've experimented with new sensors there because it's just like it's less of a loss if it goes wrong. And also because we have like our practice robot and our main robot, we're able to like test things on one robot while not having like the change on the other robot in case it was bad, and we can always go back.
And we tend to stay with the same part as long as there's like not an obvious like problem. But like for example, this year we're working on using a new processor for our vision that's more powerful instead of a rock-by, because it allows us to do like more complex machine learning and like software vision.
Yeah, so we're doing that in our off season as well. So I guess it's just a good time for us to experiment with new things and learn.
Thanks.
Yeah,
Thank
thank
you.
you.